Okay, here is appendix number 2, and you notice you don't need to know this for the exam, but I know that there are people watching these videos that say, well, where does that circular speed come from? Well, I'm glad that you asked, okay? Because what you do is you set centripetal force for an object going around in a circle equal to the force of gravity. Okay, you're going to take those two equations, set them equal to each other, and then solve for the letter V, and then that turns out to be the circular speed of an object going around a star. Or it could be the circular speed of a rocket ship going around the Earth. Well, there was a second kind of speed, and that was the escape speed. So where does the escape speed come from? Okay, this time we're going to set the kinetic energy of an object equal to its potential energy. Do you remember that if the two of them were equal to each other and you got 0, then you would be traveling at the escape velocity. So we're going to set the kinetic energy, which is 1/2 mv squared, equal to the potential energy, and then again solve it for the letter V, and then that's where you get the escape velocity from. You notice the two formulas are almost identical. So if we go back to this one and then we compare it to this one, the only difference is a factor of 2. So that the escape velocity is the square root of 2 times the circular speed. Okay, so let's now calculate the actual orbits for a couple of things. So here I calculate the total energy that the Earth has in its orbit around the Sun. So what did I do? By knowing how long it takes the Earth to go around the Sun, and by knowing the distance from the Sun to the Earth, I can figure out the speed of the Earth as it goes around the Sun. So once I've got the speed, I then can plug it into kinetic energy. So the kinetic energy is going to be 1/2 the mass of the Earth times the speed of the Earth squared. And there it is. Okay, then I calculated the potential energy of the Earth. So what would I need to know? I need to, again, know the distance from the Sun to the Earth, and I need to know the mass of the Sun. I need to know the mass of the Earth, and so I plug it into the potential energy equation, and I get another number. Notice the kinetic energy is positive and the potential energy is negative. And then I add them. So the total energy, put the two together, and notice you get a negative number. So what's the significance? A negative energy means it cannot escape. So we don't have to worry about the Earth going flying off into outer space. It will continue to orbit around the Sun because it doesn't have what kind of velocity? Escape velocity. Okay, so I wanted to do it for something that did escape. And so that is going to be Voyager 1. So Voyager 1 is a space probe that we launched a long time ago. And currently it's heading out of our solar system into deep space. So I did the same thing. I calculated what is the speed of Voyager 1 and then used that to figure out the kinetic energy of Voyager 1. And then I calculated the potential energy of Voyager 1. And then I added them together, and notice this time it's a positive number. So what does a positive total energy mean? It's escaping. So Voyager 1 is currently escaping the gravity of the sun and is never going to return. Now, interestingly, Voyager 1 is on a direct path for a black hole. And so in the future, it's going to fall into that black hole. It's going to go through a wormhole. It's going to come out on the other side of our galaxy. It's going to be adopted by a race of machines who are then going to build a gigantic spaceship around the probe and then send it back to Earth as Voyager, and it's only Captain Kirk and the Enterprise in Star Trek the Motion Picture will be able to stop it. It's true. It's going to happen, okay? Science. All right, so let's take a quiz. So let's take a break. When we come back, we will take a quiz over what you have learned today.